Bo jeszcze wczoraj byłam na w Planetarium Śląskim na 70-leciu. Wiedzieli. So good afternoon, everyone. Can we start? Thank you. So today we are hosting the person that spent quite a lot of time here at this observatory, Professor Izabela Kowalska-Leszczyńska. Izabela did her master's here. She also did her PhD here. She was working on gravitational waves research, and then she moved to Center of Space Research. Space Research Center, exactly. So CBK here in Warsaw, and she's working on some more heliospheric stuff. And she's gonna tell us about a very exciting experiment that she's leading. It's called, well, she's co-leading. She's one of the leaders in the group working there. It's a purely Polish experiment and the NASA mission. And that was recently launched, and we're gonna hear about some news related to the experiment and some research that's gonna be done with this satellite and instrument, right? So the floor is yours. Thank you.
So good afternoon. Thank you for that very kind introduction, and thank you very much for the invitation. It is always a great pleasure to be here again. Before I begin, I should apologize and maybe explain myself a little bit. I said that I will show the first results from GLOWS, and I really wanted to do that. Unfortunately, I'm not able to because NASA put some restrictions, and they wanted to announce results from all 10 instruments together, and it will happen next week. So unfortunately, I won't be able to show the exact results that we got, the first slide. Although I will show some predictions, and I would say that the predictions are very close to what we actually saw. So maybe this will be enough. In next week, in our social media on Facebook or somewhere, this slide curve should be available, so you can just pick if you're interested. So, first of all, I will start with this. This will be not the first slide, but the update on the Polish photometer on the IMAP mission. Later on, I will explain all those things. But let me start with a brief introduction and the big picture to set a stage for GLOWS experiment. We are going to research and to study heliosphere. The heliosphere is well, you can imagine it as a bubble-like structure that is filled with solar wind. And this structure is quite big. Inside there is a whole solar system. And there is a boundary of this heliosphere, which is called heliopause. And this is the place where solar wind meets interstellar medium from the outside. This structure is some kind of shield that is shielding us from the outside particles, mainly very energetic particles, and it makes our environment inside very cozy. Some predictions say that this is the one of the reasons that life on Earth could evolve uninterrupted for so many years. Yeah, I don't know if you see the picture very clearly, but this is just artistic impression of what is going on. Okay, so the main factor that influence the shape of the heliosphere and how it behaves, how big it is solar wind. Solar wind itself, the term of solar wind, exactly those words, were proposed by Eugene Parker in late 50s, the 20th centuries. In his paper, because he actually predicted that in his solar atmosphere model, the corona, the atmosphere of the sun, should be so hot that those particles should escape from the gravity of the sun. And he predicted that this constant flow from the sun should be supersonic with speed around 500 to 1,000 kilometers per second. At first in the community, this was not very popular. And actually the first paper of Parker was rejected by reviewers. But later on, observations of comets and then interstellar missions to Venus, for example, showed that solar wind is actually there. And there are very, very fast particles escaping the sun, and it's some kind of constant flow from the whole sun. Solar wind is composed, made of particles that are ions, so mainly protons, electrons, and alpha particles. And we have actually two types of solar wind. So there is a slow solar wind with speed around 400 kilometers per second, and then there is fast solar wind, which is 2 times faster, and it can reach even 800 kilometers per second. And as you can see on this plot, the structure of the solar wind, the latitudinal structure, is very different depending on the solar wind of the solar activity phase. So this plot was done during the solar minimum, and this is the solar wind speed. As you can see in the ecliptic plane, the equator, we have slow solar wind, and on higher latitudes we have very fast solar wind. And in solar minimum, the structure is very clear. During solar maximum, there is no such a structure. We have solar wind slow, fast, and everywhere. And it is basically very, very chaotic during this phase. So the reason why is that is still unknown. We're still trying to uncover what is going on inside the sun, and measuring the solar wind properties at different stages, but also trying to see how the magnetic structures are evolving during the solar cycle. Of course, solar wind can be solar wind affects our planet. For example, it can affect satellites or Earth grid infrastructure, and also it can produce very beautiful aurora borealis, which is I would say the only positive thing that that goes from solar wind and those energetic particles. So geomagnetic field of our planet is shielding us from most of those particles, and this is another reason why life can be safe inside this shield. On the other hand, we have interstellar matter outside the heliosphere, and the sun is going through this interstellar matter because it's orbiting in the galaxy. This matter is partially ionized, and it originates in supernova explosions that happened long time ago. So we have probably different bubbles expanding, and the recent findings show that actually right now we can be in that mixed region between two clouds, and that's why we see different velocities of the inflowing material. And the models showing this are has to be very complicated. It's not just one set of parameters. So to explore heliosphere, we need different sources of observations. We need to observe sun from one side because we need to know about the solar wind and the how it evolves and how it expands the heliosphere as a whole. On the other hand, we need to study interstellar matter. We need to know what is outside because well, you can imagine it as a blowing the balloon inside the room where there is air, and then you can try to blow the same balloon in the water. So you know there's a completely different thing. So the outside environment is also very, very crucial to the shape and size of the heliosphere. And we have numerical modeling that is filling the gaps between the observations, but also it has to agree with those observations. So there are a lot of models right now on the market that are treating the heliosphere as a whole, and a few models that are trying to see in the smaller scale what is going on by tracking the particles, every particle inside the heliosphere. Okay, on the next few slides, I would like to convince you that the IMAP mission, which stands for Interstellar Mapping and Acceleration Probe, is well, all in one. It has 10 instruments that can actually be treated as a one big heliospheric observatory and can measure different aspects of the heliosphere research, sun and the interstellar matter and the magnetic field inside. And all those things we can combine together and see the whole picture and try to model and develop a new view of the heliosphere as a whole. It is good that all of them are on one place because it's easier to interpret the data when the instruments are on the one satellite. In the corner there was I don't know if I can. There's an animation showing you how the IMAP. Okay, it's not very good visible, but those are 10 instruments, and you can see the field of view of those instruments while the spacecraft is spinning. IMAP is a satellite which is right now on its way to the L1 Lagrange point, and it will be spinning, and the axis will be pointing 4 degrees from the sun. And those 10 instruments will be observing the solar wind and other things. On the next, yeah. So this is the main goal of the mission are those 3 points. We have 10 instruments working together, and we want to solve some questions that are not answered yet. So first of all, we want to understand how the acceleration of particles in solar wind happens, how those particles are accelerated to those speeds that we actually observe. Then we want to map the interaction of those particles, high energetic particles from solar wind. When they go outside the heliosphere, they interact with the interstellar medium, and we can map those interactions using remote sensing instruments on board IMAP. And the last one is that we can sample the local interstellar medium, because some of those particles from the outside, the neutral part of interstellar medium, can just go inside the heliosphere and penetrate it. And we can actually catch those particles if they are not ionized on the way. Yeah, IMAP was launched on September 21st on the Falcon 9 rocket from the Florida. If you are interested about the whole mission and details about it. There's an IMAP paper very recently published, and also there's an IMAP book that is coming very soon. In this book, there will be separate paper on each instrument, and then there will be thematic theme papers about the new science that will be done using different instruments altogether. Okay, so particle accelerations. We know that from the sun there are different types of energetic particles during the CMEs, during the other very violent eruptions, and they have different energies. So we have on the board of IMAP well, actually there are 3 instruments, but one of them probably has 2 detectors inside, and they will be tracking those different particles. And we know that there is some connection between accelerated particles from the sun and the energetic particles that are created on the boundary of the heliosphere. Those energetic particles from outside, not outside, created almost outside of the heliosphere, will be observed by the other instruments, IMAP low, high, and ultra. And our goal is to understand the fundamental link between those two by measuring both of them and find some correlations. Of course, there's a MAC instrument, which is a magnetometer, and of course, this is very crucial for every acceleration processes if we are talking about charged particles. Another very important part of the IMAP mission will be so-called iAlert. 5 of the in situ instruments, which will be measuring solar wind particles directly, will be combined with the NASA Deep Space Network, and it will be in real time broadcasting the data to space weather research. We want to support the safety of the satellite infrastructure and also the all those space weather things that are going on. There are a few different satellites who also is involved in this iAlert, and so we will have 24-hour data about the space weather, space conditions all the time. Okay. Może pyk? Oh. Okay. The mapping of the interactions outside at the border of the heliosphere will be measured by 3 different cameras, IMAP low, high, and ultra. They are measuring different, they are catching, actually they will be catching energetic neutral atoms. Those are those INA particles. Those particles are, well, when we have a particle from the solar wind, very energetic, ionized, that is traveling outside the heliosphere. At the border, there's a magnetic field, and it can meet some neutral atom from outside. In the collision, it can exchange a charge, and it became a neutral atom, but still with very high energy, because energy will not change a lot during that collision. And this energetic neutral will come back in the direction of the sun, and it can be catch by one of these detectors, depending on the energy that of this particle. So by measuring those particles, we can create a map of interactions that happened outside of our heliosphere. And here are a few animation showing you the field of view of each of those instruments and the maps that will be created during the observation. Or not. The last one is doesn't want. Oh well, the last one looked very similar, but in the higher energy. So this is basically the other satellite that is still working. It is called IBEX. It has only two detectors, IBEX low and high, and IMAP low and high, will be the enhanced version of those two detectors. So we do have some sense what we are looking for, but now we will have lower, higher resolution and cadence in a time domain. And the last type of detectors on the board, it is a dust detector. We will be catching the dust coming from outside the heliosphere. This is the biggest instrument on the IMAP, and also using IBEX, IBEX low, and IBEX low is the one that is currently working on the other satellite. IMAP low will be much more sensitive, but it will be doing basically the same thing. The enhancement here is that we have a pivot platform, so we will be looking not just only on the one direction, but we can actually move it a little bit and look at different places during the time and make much more detailed maps of the interstellar neutral atoms that are coming from the outside of the heliosphere and without any interruptions can be catched. And the main difference between INA's detections and this interstellar neutral atoms will be the energy, because interstellar neutrals will have the energy consistent with the speed of the flow, and this speed can be just calculated by knowing how sun is moving through this interstellar medium. Yeah. This is more about the dust. On the one of the seminars, someone noticed that the dust is not very. It can be confused with the dirt. So this is the definition why the dust is actually important, and it's not there. By studying dust, you can learn a lot about, well, actually everything, because it interacts with different particles in different ways. So it's very crucial to measure dust, which is not very simple, because dust can be very different sizes, and building the instrument was very challenging. But I wanted to focus on the one of those 10 instruments, mainly Global Solar Wind Structure experiment, which is GLOWS. This is the experiment I was working with, and I'm still working on it. GLOWS is Lyman alpha photometer, which means that we will be catching photons, but not any photons. We are interested only in Lyman alpha photons. Those are in the ultraviolet part of the spectrum, around 121 nanometers. So there, we cannot observe them from the Earth, of course. So we need to go to the space with our instrument. This is the actual flight model. So exactly this one is right now on the way to the L1 Lagrange point. The main target of this instrument is heliospheric hydrogen backscatter glow. Maybe I will show you the cartoon to explain what this helioglow actually is. So from the outside of the heliosphere, there is a flow of interstellar neutral hydrogen, among other species, of course, but the hydrogen is the most abundant. And those hydrogen atoms are all over the heliosphere. And when we just illuminate them by the Lyman alpha photons, this is exactly the wavelength of the excitation of the hydrogen. So electron will jump to the higher energetic state, but very soon it will go to the basic level of the energy, and then it will radiate another Lyman alpha photon. And those re-emitted photons are exactly the target of our instruments. We will be catching those photons. So heliospheric glow is like all over us. So we can just look at it as a map of this glow. And actually, there's an instrument on the SOHO satellite called SWAN that is doing exactly that. I mean, they taking maps of helioglow that you can see on the left-hand side. On this map, you see also the scanning circle of glows instrument. So we will not be doing maps. All we measure is just a stripe around the sun. And our measurement will look like the plot on the right. So it is, we call it light curve, although it's not in time, but in the spin of the domain. So what you are seeing here is what we would see if we just crop this one circle on the sky and plot it as a line in here. So those are really not close observations, those are SOHO SWAN observations, but we will expect something very similar, except that close is narrower, spectrally narrower, so we have better filter of the Lyman alpha, so we will not expect so many stars. Because you see here the Milky Way, all those stars are contaminating the actual map of the helioglow. So in our detector, we will expect less of them, but the main structure should be the same. And what we are actually expect? Well, we do have a model, heliospheric. It calls BAF helioglow model. And we use the ionization model inside, radiation pressure, background of the extraheliospheric contamination and other stuff. And we can actually produce a light curve that we are expecting. This particular light curve was simulated on the November 14th, November 14th, which was the first day we actually turned our instrument on. And on the map, you can see the scanning circle, so which part of the sky we observed at that time, and what we actually expect was two stars, not two stars, but two parts of the scanning circle will be affected by the star. On this plot, you see red line, that is our model. And you see the alpha Leo and a few stars that will give a combined signal that will be very distinguished seen on our light curve. As a comparison, the green, yeah, they are green. Green dots are the SOHO SWAN data. So you see that we are expecting much less contamination from the stars. But nevertheless, we will see few of them, and we even can identify which one we will be seeing. And actually, we do want to see some of the stars because our calibration will rely on those. UV instruments are aging, and during the time the sensitivity is going down. So we have to monitor this sensitivity loss somehow. So our idea is to see the stars, very bright stars in UV, that we'll be seeing each star twice during the year. So we can just compare a level of the signal that we saw a few months ago and now, and try to estimate what the sensitivity loss was at this beginning in this time, and develop some factor that we can rescale our other data. Actually, on this plot, there is also in the SWAN data. This is not actually not star. This was a comet, and we expect to see this comet in our data as well. Well, here, this comet was discovered on the SWAN data. I will show you the arrow there is showing you the comet. I was trying to if you see, it's very faint, but it's definitely there. So we expect to see this comet also in our data. It was very lucky because this comet was exactly at the day when we turned our instrument on. So it was very lucky. Okay, in the end, almost end, I wanted to talk a little bit about how we actually translate these light curves of helioglow into the solar wind properties, into the solar wind structure that we are actually trying to measure. So first step is to mask our light curve and get rid of all the stars, because we are not interested in them at that point. Yes, we will use them as a calibration tool, but then we just need to remove them. Then we use a machine learning that was trained on SWAN data, and we can obtain total ionization profile. By total ionization, I mean every possible ionization process that is going on around the sun. So hydrogen can be ionized by electrons, by photons, by protons doing the charge exchange, and those three types are together in that plot. Then the most interesting part is charge exchange, because this is interaction with protons, and we actually want to measure the density and speed of those protons. So this is the only type of ionization that we are interested in. So from the total ionization rate, we have to subtract photon ionization rate. Right now, we are just assuming that electron ionization rate can be well, neglected. And photoionization rate is here very simple. It doesn't take into account any anisotropy. We just assume that that sun is shining basically the same and spherically symmetrical, which is not the case actually. But in later parts of our project, we will be adding new complications. So far, it is spherically symmetrical, and there is no electron ionization in the first attempt in the pipeline. Once you have charge exchange, you can solve a set of equations. Most of those things are very well known physical constants or physical parameters that are very easy to measure. So solving this set of equation numerically is not very complicated. And then we will end up with solar wind speed profile and solar wind density profile. Why the profiles are so important? Well, right now we are observing usually the ecliptic plane and the equator of our star. So we have a lot of information what is going on with solar wind from the equator. But from the poles, we don't have so many informations. There was Ulysses who took few pictures of the solar wind outside the ecliptic plane, and now there's Solar Orbiter, which is also glimpsing on the poles a little bit. But using our method, we can infer the whole structure, latitudinal structure from the poles from one pole to other and everything in between, observing the helioglow basically every day. So we will have a much higher cadence, and we will be able to monitor it in a long period of time. So those results should be very, very valuable. Okay, and actually it is almost the end of my presentation. I wanted to show you the real picture of IMAP. It was taken before the launch, obviously. This is I'm talking about the middle picture where there's a vacuum chamber and IMAP is going inside to be tested in the vacuum environment. There are solar panels, and this picture is from the lounge itself. Yeah. This is my boss, Maciej Bzowski, on the left, the smaller one, and the other guy is David McThomas, who is the PI of the whole IMAP. And this picture was taken during this, I would say, after the launch. On the next photo, there are our IMAP instrument engineerings. All from all the instruments. One of them is our guy. I don't know why this stopped working because I wanted to show you one of our engineer. Here is Jakub Mądry, and he is GLOW's operator, so he knows a lot about the instrument and how it works. And he's the guy who couldn't sleep. I mean, during all those tests that were during the night. I don't know because this is the film from the start. It's only 2 minutes long, but I don't know if you will hear something. The sound will be. Nope. No, you cannot hear it.
But we can read.
It was after the sunrise, so it was very beautiful scenery.
That was from Cape Town.
Yes. This was my first and only launch that I saw personally. Yes. And it is much more exciting being there. I mean,
It's a big distance, right? So.
Yes.
But could you hear stuff when we were there?
Yeah, yes. Actually, the launches on Cape Canaveral are once in few days. So during our stay, we hear a few of them. And during the night in the hotel, it's actually all vibrating. Yes. So
How far? From the starting point.
Few kilometers. You can watch it from.
yeah. My boss was in better place than me, but
Then because you can observe it from the beach, right? So because you can go to the beach and look at the rockets that start.
yes.
But if it's delayed, it's very nice.
But, oops, no. Okay. The whole IMAP is a collaboration of several institutions, most of them from US. There are only two institutions from Europe. One of them is Imperial College of London. They developed MAC instrument, the magnetometer. And the second one is CBK, our own institution. And actually, really?
Under Imperial College, of course.
Oh yeah, but they do not have hardware input.
Wow.
You know what? I'm showing that like 5th or 6th time. And you're the only one who noticed. Actually, I didn't notice.
There's also burn.
Yes, yes. We have collaborators from there, but they are not developing the instrument or even a part of the instrument. But they are just collaborating. But yes. So most of the instruments are in US. Only two of them are were built in.
Yeah, you are right too, from Europe, because UK is not Europe.
Oh well.
Also,
Don't look at it so closely. Sorry. My point was that we were invited to a very unique opportunity. We are giving very unique opportunity to build and design a whole instrument on the NASA mission. CBK and Poland in general is doing a lot of missions, a lot of projects inside the ESA. Because we are part of the ESA, obviously. So this is not a very new thing. We have a very experienced team of engineers, but this was the first time when we got a whole instrument by ourselves, and we did it for the first time. Our engineers never done the UV photometer before. And also we collaborated with many private firms from Poland in the development of the software, for example, and parts of hardware that we designed, they just manufactured. So it was a unique opportunity for all the space sector in Poland. And next week, about the time we will be able to show the actual results from all 10 instruments, among them from GLOWS. But as I said, we actually saw very similar thing to what we expected. So we are very happy because our models are okay, and also our sensitivity is much more or less what we expected, and it is better. I mean, the spectral sensitivity is better than SWAN, so everything is looking very good. Okay, thank you. Don't.
Thank you, Izabela. Thank you. Well, congratulations. The last slide to show, that's good. Congratulations on delivering great instruments, because like a lot of instrument that Polish companies are building are not for science. So this is the research one. So also congratulations to the entire team, especially to the scientists who proposed it and then the engineers who delivered. So we fingers crossed for all the results. Do we have any questions or comments?
I have a question. When you showed this slide with the light curve, you showed your model was very smooth compared to the observation from Soho. Why is that?
I mean, this one,
yes,
for example.
Yes.
So the shape, well, because of the different calibrations, if you just draw it like the rough data, they will be on the different levels, of course. But then we can normalize it, and we will see that the shapes are agreeing. It is because we have a very good model of helioglow, and they are observing helioglow. So yeah. Although we don't have in our model, we don't have the variable background from from galactic background, basically. So this is we are working on it right now.
Actually, I had a question about the background because you said that the heliosphere is influenced by the wind, solar wind, but also by the background. Is the variability of the background will be observed during the mission, or its time scale are not compared?
Well, this background that we will be observing from the galactic background is mainly because of the hydrogen. I mean, there's a lot of hydrogen everywhere. And also the bright UV stars will contribute a little bit. And the bright ones we will see in our light curve just as a peak. But there are a lot of stars in UV that we will not see as a peak, just as a rise in the signal that will be unresolved.
Yeah.
And no, it should not be variable in the shorter scales.
So talking about timescales, on what timescale the helioglow changes and how it compares to the spin period of the satellite?
Okay. Basically, it is changing. The helioglow as a whole is changing during the solar cycle timescales. But our spacecraft will be traveling around the sun with Earth and with L1, and looking at the helioglow from different points will show us different picture. So, for example, if you look at the helioglow and the inflow of the material is in your face, as I would say, then we expect very symmetric picture. But if you look at it from the side, then there will be different brightness, and the contrast will be much higher. So the helioglow as a whole is changing in the solar cycle, but we will be in different positions. So we will be seeing different pictures day by day, basically. It's not very fast because the orbit is very long. Well, a year long, but you see a very different picture a month apart.
What's this?
The spin period, it's fast. I mean, it's like seconds. So I don't remember exactly, but it's fast.
Sorry, maybe I didn't get it. How long the satellite will be operating?
So the main mission is 2 years, of course, but then there will be extensions. I hope. We will hope. Well, the previous satellite, the CBK I was mentioning, it also had 2 years expected time, but it's working until now and was launched in 2008. So extension was very, because if everything is working, then why not?
Okay, especially now.
Yeah, that could be tricky. But hopefully we want at least one solar cycle.
Any more comments? I was also wondering about the IMAP itself, because we get used to the space telescopes, let's say, that have mirror, so as bigger and better, and then different instruments that do different things, but we're using one mirror. But IMAP, as I understand, it's like just the one platform that holds several instruments, and all of the instruments is like a little kind of telescope or detector, they're independent completely, yeah? Okay, so only
Yes.
like the power and some navigation
Power supply
things,
and the fuel is
is the common, and also the transmission to the earth, and but they are working like there's no common mirror or something like this is that they use. Okay.
yes. Although there are a few instruments that are tube detectors. To tubes looking in different directions.
Okay. That's perfect. Okay, I didn't see more questions, so let's thank Isa. Thank you very much. And we are looking forward to the press release, the first results and all the results.
Me too, me too.
Yes, so next week we're gonna have a seminar that is more historical. It's gonna be about the instruments at the observatory, Warsaw Observatory. It's gonna be given